Good day, everybody, no matter where you are or what you're doing. This is the second day in the 2024 Artificial Intelligence Conference, the premier global gathering for AI enthusiasts, professionals, and thought leaders. Thank you for joining us. And we want to extend our gratitude for your expertise and your time in really honing in your skills. AI developments and insights aren't just for now, they're paving the way for the future. They're shaping the technology for us in business as we are now and for the next 50, 100 years. It's a pleasure to introduce my next guest and welcome him to the stage, Ilan Shaviv, where he has got the expertise in really homing in the innovation within the future. Ilan, please welcome to the stage. And how are you today?
Thank you, Buzz. If I may share my screen and start presenting.
Of course.
Okay. So my name is Ilan Shaviv, and I'm the CTO of Imagery. And if I may, Imagery was established in 2015 as a high-end vision computer application, and in 2018 we started specializing in the automotive sector, creating autonomous driving software using AI for HD mapless driving system, which is inspired by bio-inspired by two ways, and when we are real-time perceiving the environment, and as well as motion planning using artificial intelligence. Okay, so today's topic is, well, I'm going to talk how AI enables the autonomous vehicle to drive, and specifically how AI is used to understand the video feeds, and then make decisions using AI to do that. But a small disclaimer is that the term AI has been coined in the 1950s, and it includes a large set of tools. And in this lecture, I'm going to use AI as simply a synonym for a neural network or deep neural networks, which is basically what AI is today. Neural networks that mimic the human brain. Okay, so let's start with see how the information flow of the autonomous software works, and everything starts with sensors. We have a series of sensors, cameras, radars, lidars, that feed information to a neural network. Okay, this might be one neural network or a series of neural networks, and their sole purpose is to do two things. One is to detect objects in space around the vehicle, and then segment the image to information where's the road, where are crosswalks and lanes, and so forth. Okay. Now the segmented image needs to be projected and then stitched between the various sensors that we have around the vehicle to create a blank map around the vehicle. Now, going back to the detected objects, these objects need to be tracked in time, and then everything is to be placed on this surround map around the vehicle. Now, to pause here for a minute and demonstrate what we just learned, we can see here 3 of the 8 cameras that we have on the vehicle. And as you can see, the image segmentation here, we have the road is segmented with marked in red, have the crosswalk in yellow, and stop line, and everything that's around the vehicle. And here we're starting a stretch of road, a straight stretch of road with 3 lanes, and the leftmost lane is a public transportation lane, and it's marked in yellow. And if we take all this information now, play it over, we can see this surround map around the vehicle with the tracked objects appearing on the map. And this allows the vehicle to now go to the second part, which is start planning to plan a route to process this information. But if we go back to our diagram, image segmentation in real time sometimes is hard, okay? And you may opt to use a shortcut of having someone map beforehand everything around the vehicle, around the city, and you have that is called an HD, high definition map information around, and with precise localization information where the car is at every moment, you can create this blank map in order to occupy it with the tracked objects that you find. But shortcuts have their price, and we'll talk about this later in this lecture. Okay, going back to the diagram. Okay, we have the objects that we're tracking, and we need to understand another word about the objects that we're detecting. We should know that the neural networks are very good at detecting stuff or objects that it had seen in the past. And that is, if we have this interesting image here, we can see here all the vehicles that it has detected, as well as this partly occluded vehicle. But this is something it has never seen. And as something new, the neural network has a problem identifying it. And if it does not know how to identify it, for the system, it is considered as not being there. Okay, so we need to augment the system with an unknown object system that will be able to detect this unknown object. So the system basically will know there is something there. I do not want to drive through it. I don't really care what it is. I just want to know that I don't want to drive through it. Okay. And again, it's tracked in time and placed on the surround map around the vehicle. Okay. So now that we have a surround map around the vehicle, we need to create a motion plan to traverse this surround map. Okay. Returning back to our example from the beginning, here we have a straight stretch of road, not so interesting. And analyzing the surround map that we get, we have three lanes, all of them going straight, and we would expect the motion planner to give us a trajectory here marked in blue for the car to carry out an exercise. Okay, but again, remember we have 2 lanes here. Okay, and the motion planning could also create a path which is switch 1 lane to the left. Okay, but the motion planner, in order to actually carry out this information, needs to get some help from outside, called an intent manager, which is fed from a navigation layer, which is actually a directions to tell the car how to get to its destination, its point B. Okay, the map is a short area of the field, and the navigation layer is top layer saying either go left or right, or in order to get your destination. Now, changing lane is a simple task, and then we can go. It's more interesting when we get to an intersection. Here we have a path like turn right in this next intersection, or we can have a path going straight if destination B would be somewhere in front of the vehicle. Okay, and then going straight isn't always straight, and sometimes straight is about curvy, and it's still straight, or it makes life interesting. Okay, now again, the motion planner, the goal of the motion planner is to create a trajectory, like we said here, marked in blue. And this trajectory is later fed out to the vehicle controller, which creates commands to the car, the throttle, the brake, and steering commands for the car to follow this trajectory. Okay, so this is the full information flow diagram that we expect to see in an autonomous vehicle software stack. But if we zoom out for a minute, we see three basic steps. We have the perception, we have the motion planning, and we have the vehicle control. The perception may be either using HD map or HD mapless, as I stated before. And if we analyze the using HD map, obviously the pros is simpler to implement. You are able to see around corners because somebody already mapped the city for you. But the cons are that you're dependent on communication. You need to see, this is a lot of information to download from the cloud. And when you have that information, you have a problem of obsolete data. Map information is, you don't know if map was created yesterday, a week ago, or even maybe a year ago. And then you need to augment your system with some kind of perception system to verify this data that you got. And then you have always the problem of the two clocks. When you have two clocks, you do not know what is the exact time. Okay, and you need perception localization in order to know exactly which area of the map to cut out for you. And since you have communication, there's always the issue of some kind of cyber vulnerability. Switching to HD mapless, we will need to switch also the pros and the cons. And again, it's not simple, it's complex, sorry. And you don't see around corners, you only see what the car sees, which is basically exactly like a human driver. And we aim to replace the human driver, so this should be okay. And you also need to create real-time onboard perception. Kind of hard, okay? But the upside is you're self-sufficient. You don't depend on communication, and you don't have a problem with all data. There's no data to be concerned about, so you don't need to verify that data. And you can use only loose localization, which may be just for directions, how to go right or left, or how to get to your point from A to B destination. And since you do not have communication, you're much more cyber robust. Switching to motion planning, there's the classical rule-based motion planning, which is basically writing what if then for every situation that you see. The pro for that thing is it's much more explainable. When you're reaching these safety guys and regulation guys, they really like explainability. And the downside is that it's a lot harder to adapt to new unseen situations, which is actually the plus side for neural networks. They are very capable of adapting and interpolating between two known situations that it's trying to get a new unknown situation, but you pay with the explainability problem. Okay. Again, that's not the only approach. If we notice that the perception is neural network and the motion planning it should be neural network, there's some people suggest that how about replace that with one big neural network. The pros are that, again, you can apply, it's a lot easier to apply unsupervised learning technique, And unsupervised meaning that you can use unlabeled data, which is usually the problem with neural networks with teaching, that is saves a lot of money and a lot of time to create the data. On the downside, you have one big black box that you don't know exactly what's happening here. And I'm sorry, I should have also removed the surround map. You don't have information what's going on in the middle. You just have input and output. You need a big computer to process that. You need a big computer on the target machine, on the vehicle, with a lots of tera operations per second, tops. And you need even a bigger computer to train your network, and a lot more data to process in the training. Okay, so and then you have like maintenance problem. Say you have problems with identifying a stop sign. What do? The solution is always, well, add more data. So I add more data of stop signs, and now I need to retrain the whole system again. When I retrain the whole system again, I get a new neural network that does everything possibly better. But I need to now verify again the stop signs that I understood it's not working. But I also need to verify everything I already proved that's working. Say the previous network processed better pedestrians and vehicles, but now I need to reprove it because it's a new network. So maintenance is a problem. It's a engineering nightmare. Okay. Again, since we don't have any kind of signals in the middle, we cannot intervene in the middle and do a lot of stuff that might be useful. And again, the bigger the network, the harder to explain. Now, there is an approach of saying, hey, if we use one big neural network here, why stop here and not do also the controller with even a bigger neural network? There is there are rumors that this is Tesla's FSD12 approach to the solution, but this is like a big mid grinder, and apologies, but it's a big mid grinder that you fit in images from one side, expect the car to learn how to create commands to the vehicle without doing it, without alleviating anything from the network. So it basically a really big network. Okay, returning back to the multi-step modular approach. Okay, we can see that the pros are that we have multiple networks. It allows some form of traceability, understanding what's going on between the networks, and hence it's a lot easier to maintain and identify the weakest link and how to change to strengthen the network, the system, by strengthening that specific weak link without modifying the other networks. And you can modify stuff in the middle. Say you have a system that was trained to drive in the US, and now you are asked to drive in the UK. That is a system that learned to drive on the right side of the road, and now it needs to drive on the left side of the road. Do you retrain everything from start, or do you tweak in the middle and start driving from the first day that you arrive there? Again, the problem is that you need some coding. It's not a big box that you magically train, and you do need to understand what you're doing. So you need to do some coding. To sum up, we have some do's and don'ts. You do not use HD map data. It's unscalable. Generative AI, well, we have rules how to drive. Hence, I don't think there's room for creativity. you have strict rules. If you don't abide by the rules, there will be a police man or woman to stop you and detain you. Unsupervised learning, don't do that. You need some safety concerns. You need to understand exactly what's going in and understand what kind of driving that you're feeding it. On the upside, do a lot of neural networks for perception, many small neural networks. It's a lot easier to maintain, less data needed for training because it's smaller network, and it's much more simpler to certify and approve because it's much more smaller boxes and you can approve box by box. And motion planning, do that with neural networks. There are a lot of new edge corner cases and long tail problems that neural networks are have a much more easier way to adapt and provide a solution. So AI is the key to achieving level 3, level 4 solution, autonomous vehicle solution. And you want it to be location independent. So you don't want to use HD maps. We're driving in mixed urban traffic in 4 countries, 4 continents, sorry, and we're driving also on both sides of the road with the same network, using cameras only, and which renders a low-cost solution for mass market. Thank you.
Ivan, that is next level, to say the least. What made you come into this industry? I mean, this is so unique. I've got Elon Musk running through my brain all the time you were speaking.
It's a different Ilan.
Yeah, of course. And this is what I was about to go into, because he's in over there and you're sort of doing your thing with LiDAR and things like this. How did you come across this? Short version.
I like a challenge.
Okay, apparently.
Yeah.
So, if people are trying to get hold of you, where is the best place to find you? How do they get in contact?
I believe my contact information will be on the email, on the site, imagery site. Please go to the imagery site and see whatever. All the contacts is there.
Are you on LinkedIn?
Yes.
Okay, well, so if you're looking for Ilan and you want to look into autonomy travel and LiDAR, he's the guy to go to. Go to LinkedIn, go to the website. For myself, Ilan, it's been a privilege to have you here and host you. From myself, have a wonderful day. Be safe and be well.
Thank you, Buzz. It's been a privilege being here.
Thank you.